In this video, we're going to look at how to simplify radicals. And we have four properties of radicals here, or four rules for radicals. And these just come from the rules for exponents and fractional exponents, only now instead of writing them with exponents, we're writing them with a radical sign. So if we have the nth root of a to the power of n in rule number 1 here, that's the same as the nth root of a all to the power of n. Notice the bracket can be around the root, or we can take the exponent inside the bracket, or inside the root, where the bracket would be like that. And either way, the answer is A. So we have one example over here. The square root of 4 squared is 4, and that would be the equivalent of the square root of 4 all squared, which is also 4. And then we have three more rules. If we multiply two radicals that have the same index. So index, that's what the n here is. We have that written up top here. And it's called the order of the index. So if the index is the same, well, we can just multiply a and b. If we have two different indexes here, or two radicals, even if the indexes are the same, we can multiply the indexes or the orders together to get m times n, the root of a. And finally, if we're dividing two radicals with the same index here, well, we can just divide inside one big radical. And we do use this rule a lot to break apart or break open the radicals to simplify. And of course, this is only true in the case where b is not equal to 0, because then we'd have something undefined. Notice these rules are all written for multiplication and division. Very, very important. When you multiply two things, yeah, we can break apart the root because they're being multiplied. That's what rule 2 was. But if we're adding, then the root has to stay over the sum. These two are joined together. They have to stay together. We can't take them apart. So if you're stuck and you're not sure if you can do it, well, something that I usually suggest is try to do something. Say, we know the root of 2 plus 2 is the root of 4, which is 2. But does that equal the root of 2 plus the root of 2? Can I break it apart? And if you work this out, this does not equal 2. It actually equals more than 2, 2.8. So you need to be careful, and if you're not sure if you can do it or not, try it with two numbers and see if it works. Clearly here this doesn't, because we're not allowed to open up the root if there's an addition or a subtraction. Simplifying radicals is what we're going to do here. So we want to remove all the perfect nth power factors, which means remove all the perfect squares, perfect cubes, perfect fourths, etc. And if possible, we're going to reduce the order of the radical. So see if we can make that little n in front a smaller number. So we'll do these examples here. So root 72, well, 72 is the root of 36 times the root of 2, because 72 is 36 times 2. And why did we choose 36? Well, 36 is the biggest perfect square that divides 72. So that's 6 root 2. And it helps if you know the perfect squares. So the perfect squares are 1 squared is 1, 2 squared is 4, then we get 3 squared, 4 squared, 5 squared, 6 squared, so that was the biggest one that divided there, 7 squared, 8 squared, and we should know all the way up to about 12 squared at least, which is 144. And you'd be able to do most of these knowing up to 144. So let's keep going here. We have here a cubed. So what we can do here is we can rewrite this as a squared and a. And we're going to leave b squared. And the reason we leave squared is because a squared is a perfect square. So what's the square root of a squared? Well, rule 1 we saw above, that would just be a. Root a we can't do anything with. Square root of b squared is just b. So ab root a. Perfect cubes, so these were x squared. These can be x cubed. Well, the perfect cubes, those are 1, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125, and that's probably enough to be familiar with. You can find all of them on your calculator, of course. So the largest one that divides 40, because here we're looking for cube, well, that would be 8. So cube root of 8, cube root of 5, that gives us 2 cube root of 5. Fifth roots, we don't use fifth roots a lot. The largest fifth root that can divide 64, well, 1 to the power 5 is 1. 2 to the power 5 is 32. 3 to the power 5 is much larger. So the largest is going to be 32. So we get fifth root of 32 and fifth root of 2. Notice we're breaking apart the 64 into 32 times 2. X to the 8, well, that's the fifth root of x to the 5 and the fifth root of x cubed. Y to the 12, that's going to be the fifth root of y to the 10 and the fifth root of y squared. If we simplify this, this one's 2, so we took care of that one. Fifth root of x to the 5 is just x, so that one's gone. Fifth root of y 10, well, 10 is divisible evenly by 5, so this is going to actually leave us y squared. If you think to your fractional exponents, this is the same as y to the 10 over 5, which is y squared. So those are gone, and we're left with the 3 that can't be simplified, 2, x cubed, y squared, and those can all go back under the fifth root. In example E now, we're going to reduce the power here. So this is going to give us the fourth root of the square root, and I'm going to write the 2, even though we should be aware that if the 2 is not written, or if there's nothing written, it means 2. So we get that. Because if we multiply 4 and 2, we get 8. But the square root of 16, well, we know that. That's the fourth root of 4 now. Well, we can still reduce the index 4 here as the square root of the square root, or index 2 times index 2 gives us 4. And we know the square root of 4 is 2, so the answer in simplified form is simply root 2. And so that's how we reduce the index. In this next one then, the square root of the square root of 9 over the square root of 3. Well, square root of 9 is 3, so that's simply the square root of 3 over the square root of 3, which is 1. And the last example then for this topic, 6th root of 8. And there's two ways to do this. We can say the cube root of the square root of 8 over root 7, or we can do the square root of the cube root of 8 over root 7. Because in either case, 3 times 2 is 6, 2 times 3 is 6. So both of these are equivalent, but only one is going to help us. We do not know the square root of 8. We can't simplify that, or it doesn't give us a whole number anyway. The cube root of 8, however, is exactly 2. So this one is a much more useful way to rewrite it. So this is the square root of 2 over the square root of 7. And we don't tend to like radicals in the bottom here. We're going to see in the next lesson that we're actually going to rationalize these. And we're going to try to get rid of the root 7. And let's just show you a little preview of what that's going to be. Remember, we can multiply top and bottom by whatever we want. And so if we multiply by root 7 over root 7, what happens is root 7 times root 7 is root 49, which is 7. And root 2 times root 7, well, that's the square root of 14. And so those two statements are also equivalent. And that's called rationalizing the denominator, which we'll see in a couple of videos' time. So that's it for that video. Little long to go through those examples, but hopefully you get the correct answer, you understand where those answers are coming from. Try some more practice, and we'll see you in the next lesson.